Hi, in this video, we want to take a look at data prep for Bayesian networks, specifically the directed acyclic graphs that are built using the bnlearn package. All right, so the bnlearn package gives us a function that's called preprocess. And this is a very good function in R for preparing or for taking numeric data and converting it to discrete categories. And so what we want to do today, we want to take a look at the techniques that the preprocess function gives us and compare how models do with the different types of data prep. So remember, if I'm working on a big project, it's not, a lot of us, like when we talk about machine learning and machine intelligence and stuff like that, we tend to focus on the models. The models are like front and center because that's the sexy part. That's the sexy part of machine learning and data mining and all that. But honestly, if we're being honest with ourselves, if we're truly digging into being good with data analytics, the processes that come before the machine learning are actually far more important. A good rule of thumb is the earlier something occurs in the data mining process, in the machine learning process, and the statistics process, the earlier it is, the more important it is. All right, so what do I mean by this? Well, if you want to get good solid data, your most important step, honestly, is your design of experiments. Before you collect the data, before you do one measurement, before you start doing statistics, you really want to have a good game plan to make sure that you get good quality data. If you do good solid design of experiments, you don't need a whole lot of observations to get a lot of information out of your data. If you have poor design of experiments, you need a lot of data to compensate. That's just how it is. All right, so then our measurement collections, where we go out and collect the observations, is one of the next steps to go through. And if you think about it, if that is a poorly executed process, my entire data set is crap. So the collection of the data is always going to be more important than data prep or in modeling. All right, well, what comes next? Well, that's going to be the data prep phase. And if I do good data prep, I'm in a much better position to make good models. If you do good design of experiments, good data collection, good data prep, weaker, simpler forms of models will outperform the stronger, the sexier versions of models, like almost always, because you have good, solid foundation to build upon. So data prep is super, super important. We don't talk about it very much because it's not very sexy. It's very tedious. It's a lot more subjective on what you should do. It's harder to measure if you did something, if you did it well. But data prep is absolutely critical to good data analytics, to good statistics, to good machine learning. Okay, so I want to go over it today, just over one type. All right, so what we're doing today, we're taking numeric data and we're converting it to categorical data. Now, honestly, I would prefer to convert the numeric data to ordinal data, but the bnlearn package does not support ordinal data in the modeling, so we're doing categorical. So the preprocess function gives us 3 ways to choose how to discretize our data. First one is interval. Interval means I'm going to take the range of my data and I'm going to chop it up into equal sub-intervals. So if I have this is the maximum and that is the minimum, or for you, this is the maximum, that's minimum. Then interval, let's say I want to have 3 intervals, what would happen is you basically break this up into 1/3 of equal length. 1/3, 1/3, 1/3. And you're not going to worry about where are the data points at all in that. This is usually the easiest one to interpret when we start talking to other people. The next one is the quantile technique. The quantile technique, what we try to do, we try to make sure that every single subinterval has an equal number of data points. Okay, so if I'm in a situation where I have skewed data, so if it's skewed like this, the tail is over here, well, end up happening is this interval will be very narrow, a little bit wider, and this one will be super, super wide. So we'll have inconsistent width of our intervals, but we'll have an equal number of data points in each one. And now next one is using mutual information to determine the cutoffs for the subintervals. And this usually performs pretty well. Today in this example, it doesn't perform as well as it has for me in the past, but this has been a very good technique for me on previous projects at work. All right, so we're going to go ahead and use the Gaussian test data from the bnlearn package. This is synthetic data. This isn't real data. That might be why it didn't turn out the way, or you'll see that the discretized techniques don't turn out the way I thought they would. Well, that might be because it's fake data. I don't know. But this presentation, this video is a good example of how you should use different data prep techniques in your modeling flow. And then you don't just try different models, you try different data prep and different models in combinations to get good models. All right, so let's go ahead and load the data. So I have to call up the bnlearn package. And the data is called Gaussian test. So here's what the data looks like. And it's supposed to be normally distributed data. And A, B, C, D, E, F, G. And I go ahead and just call the summary just so I get a feel of what's going on. On this one, I'm mainly looking at the spread and the central tendency as I look through. Now let's actually go through and convert these values into discrete values. Okay, so what we're going to do, we're going to apply the three different techniques to make numeric data into discrete data. All right, the first one that we're going to do is interval, then we're going to do quantile, and then mutual information. So we have constant subinterval width. Here, we try to get a constant number of observation in each subinterval, and here we're using mutual information. Now, I chose to have 4 subintervals. And why did I do that? Because those subintervals, when I do quantile, will correspond to the quantiles, or the quartiles, which we just looked at a moment ago. In the data, here are the quartiles. The first quartile, second quartile, third quartile, and we've got min and max. And so this is natural for us to do. If you don't know, usually going low is a good idea. There's plenty of times I actually just have 2 subintervals when I do this at work. The default is 3. All right, so let's go ahead and take a look at the output. All right, so if I look at intervals, so let's say I look at A got chopped up into these 4 intervals, and they're approximately constant width for each of these intervals. And we can see that we have different numbers in each interval. And we see the same thing as we go through. Now, when we look at quantile, you'll notice that each and every time we've got 1,250 data points in each subinterval. And that's across the board every single time as I go through, because it's doing its best to put an equal number, or is chopping up the numeric data so that we have equal number of points in each subinterval. If I go through and I subtract these 2 numbers, I subtract these 2 numbers, I subtract these 2 numbers, I'm going to get different values. If I go up here and I subtract these 2 numbers, subtract these 2 numbers, subtract these 2 numbers, and subtract these 2 numbers, I'm going to get the same number every single time. Maybe off by 0.01 or something. But practically speaking, it's going to be the same width every single time. Now for mutual information, so we have different interval widths and different number of points each time. But what it's trying to do is trying to find cutoffs where the new bins give information about the other new bins also at the same time. This one takes the longest to compute. All right, so now let's go ahead and let's build our actual Bayesian network. All right, so for this example, I went ahead and I just ran through all of them just because it doesn't take that long to run it on this data set. And what I'm going to do is I'm going to go through this vector. I'm going to pass the algorithm to a do call. So when I do a do call, what I'm saying is grab the function with this name, execute it on this item. And so we have a do call. The what is the name of the algorithm I want. And then for the args, that's a list. And the list has to, I name the items in the list to be the items I want passed into the function that is in the function that the algorithm is executing. And then we go ahead and store it. And you'll notice that I'm storing it. So I've got algorithm, and then I have data prep named because J goes over all of the different algorithms. K goes through all of the different data prep types that we have. Now, when we score the model, the bnlearn package supports directed graphs better than non-directed or partially directed. What do I mean by that? If every single time I have a connection between 2 points or 2 nodes, I have an arrow, then the bnlearn package has more features to support that model. Okay, so if I have an edge, there's no direction. If I have an arc, there is a direction. If I have an unordered graph, there are no directions at all on the graph. If I have an ordered graph, every single time I have a connection, there's an arrow between them. Partially ordered means I have a mixture of directed and non-directed edges. So because bnlearn supports supports graphs with every connection being directed, it supports those better. I'm going to go ahead, I'm going to go through and I'm going to tell R to say, hey, take this edge you've got and find a direction for it. So every time that we have, we have an edge, every time we have an arc, I'm going to tell it to go, hey, check to make sure we have it and we have a direction on here. If I don't do this, not all of the functions supporting the supporting models will be available. All right, so here I'm setting the arc. So if there's an edge, I'm saying, hey, convert it to an arc. And then here, I'm saying, hey, double check the direction I just gave you. Now, something about this, if there's already an arc there, if there's already an arc and I set it, it doesn't change anything. If I have an arc from A to B and I say set arc A to B, the model doesn't change. Now let's go ahead and score the network. So what we're going to do, remember I've got 3 different data prep techniques, and I've got something like 15-ish different algorithms. So for each of the 3 data preps and each of the 15 algorithms, I'm going to build a model because I've got the algorithm with interval. I have the same algorithm with the quantile. I have the same algorithm with the mutual information data prep. So each algorithm is getting executed 3 times. And so what I'm going to do to evaluate these models, I'm going to go through and I'm going to score them. I'm going to score them on the Bayesian information criterion. Now the Bayesian information criterion is we take the log likelihood and then I subtract a penalty term. Akaiki's information criterion is the log likelihood minus a penalty term. So they're very similar, but there's a difference in coefficients. Bayesian information criterion is a little bit harsher on the penalty. So what we want the maximum BIC possible. Now log likelihood goes through and measures the likelihood of the model matching the data. You can sense it. You can take it that way. All right, so now what this does, this is setting up a matrix to store the data. So, or to store the BICs. So I haven't actually executed them, but I'm basically just setting it up so I have a place to store each value after I compute it. Now what we're going to do here, for each of the algorithms, for each of the data prep, I'm going to take the corresponding model and I'm going to compute the BIC. And then I'm going to store it on that matrix I just built. Now here I'm sorting the matrix of stored BICs. That way it's easier for me to interpret what's going on. So let's take a look. Okay, so remember, we want the maximum value possible. Well, since everything's sorted, it's easier to spot that, like GS, IAMB, enter IAMB, IAMB, FDR, all gave the same BICs regardless of the data prep technique. And these are the weakest ones, the weakest models we have built so far. Okay, so let's scroll down a little bit. If I look here, I can see I've got Hill Climber, Taboo, RS Max 2, and MMHC are the strongest performing models by this criterion. Okay, so one thing that jumps out at me is that once again, the HC algorithm gives the best results every single time, regardless of the data prep technique. Now, which data prep technique gave us the best results? Well, if I look through here, if I look through this table, we can see that, you know, unless I'm missing something, interval gave us the best output every single time. That surprised me. I didn't expect it to happen. All right, so now let's go ahead and let's take the MMHC model with the interval data prep, and let's go ahead and graph it and see what that looks like. All right, and that is the, you know, evaluating on our training data, that is our best model for the collection that we built. All right, so the big takeaways from this lecture is that when you're doing good solid model building, data prep needs to be something similar to your model building. Remember, you're going to build a whole bunch of different models. You build like you end up building like random forests and stochastic gradient boosting, and you build a neural network, and you build a linear regression model, and you build a decision tree, and then you compare all of those. Well, something that's even more important than that model building, model checking, is the data prep going into those models. The data prep is more important. And so what you want to do, you want to have a combination. Hey, I do this data prep and I do this model. I do this data prep, I use this other model. I do this data prep, that first type of model, this data prep, that second type of model. And you go through all of the different permutations until you get the best model possible. That's all I've got for you. I hope you're having a great day. Take care and goodbye.